So we are going to look at inductors, the energy that is stored in inductor. Well, first we're going to start with the current and voltage relationship in an inductor. And then we are going to look at the power dissipated in inductor, the energy that is stored in an inductor. And we are going to discuss all of these equations and we'll do some problems. So inductor is nothing but if you take a piece of wire, basically a wire which acts as a short circuit. If you take a piece of wire and you wrap it around a pen or a pencil and then remove the pen or a pencil, and then you have a coil, that coil acts as an inductor. So from a straight piece of wire to a coil, it is the same thing. However, the properties of that wire change drastically when it goes from a straight wire into a coil. In early 1800, one of the scientists, basically, he discovered that when current passes through a conductor or inductor, a magnetic field is established around an inductor. And if this magnetic field is changing with respect to time, then a voltage can be induced in that inductor or any other inductor which comes in the close proximity of this inductor that has a magnetic field around it that is changing with respect to time. And actually that quality of changing magnetic field inducing a voltage in an inductor was discovered by Michael Faraday and Joseph Henry pretty much at the same time. And it is called Faraday's law of electromagnetic induction. So basically, if you have an inductor in a circuit, and if the circuit is, let's say you're exciting the circuit with a DC source. So when you start the DC source, initially, your energy in the current will start passing through the inductor, a magnetic field is going to establish, and the energy is going to store in that magnetic field. So in inductor, energy is stored in the magnetic field that is established in an inductor. Now, initially, this magnetic field is going to be changing for the DC circuit. And as long as this magnetic field is changing, a voltage is going to be induced across that inductor. And as you keep running the circuit, the magnetic field is going to be there, but it will stop changing with respect to time. And once that will happen, then the voltage induced in the inductor is going to go down to zero because the magnetic field is no longer changing. And at that time, we say that the circuit is working or operating at the steady state condition. If you have an AC circuit and you have inductor in the AC circuit, and since the AC voltage, AC current is always changing, then you will always have energy, the magnetic flux or magnetic field around that inductor that will be changing. And you always have a voltage across an inductor. That voltage polarity is going to be changing because your current is going to be changing and your magnetic flux is going to be changing in an inductor if your source is an AC source. And the energy is stored in the inductor. Sometime it will be stored, sometime it will be supplied based upon the cycle that your circuit is going through. So our discussion, of course, first of all, we're going to start discussing the basic voltage current relationship of inductor, power, and energy. And then we are going to use inductor in DC circuits. First, when the circuit is operating at a steady state, that is when the inductor is fully charged, but its voltage is zero. That is, your magnetic field around the inductor is no longer changing when it is at a steady state, and therefore the voltage is going to drop down to zero. However, there will be current that will be flowing through the inductor, and inductor will be acting when the voltage is zero. Inductor will be acting as a short circuit. And then we are going to, later on, we are going to use inductor and resistors in a circuit, in a DC circuit, and then we are going to observe the natural characteristics of inductor and then the force response of inductor later on. So we are going to start with the relationship between the current and voltage for an inductor, and the voltage across an inductor, VL, can be calculated using the equation L dIL over dt. That is, if the current passing through the inductor is changing with respect to time, then you will have some voltage across it. If that current becomes constant, then the voltage is going to drop down to zero. And that's what happens at the steady state. The current becomes constant because inductor starts acting as a short circuit. All the energy that is stored, it's stored there and it's no longer changing. So the voltage drops down to zero, and the current, of course, it becomes a steady state. It becomes a constant value. So the voltage also drops down to zero at a steady state. But as long as the current is changing, the voltage is going to be there across an inductor. As far as calculation of the current is concerned, we are going to use integral of the voltage. So we can use di, we can write this equation as dIL is equal to 1 over L VL times dt. And then we integrate both sides. DIL, let's say initial value of the inductor current is I naught, and at any time t, we have ILT. And then we integrate that voltage with respect to time to get the current equation. And the current equation is going to be ILT minus I naught is equal to 1 over L from initial time t naught to any time t. So the current at any time t can be given by 1 over L t naught to t VL dt plus the initial value of current at t naught, which we are calling I naught. So that's the current equation for current that is passing through an inductor. By the way, L, of course, is the inductance of the inductor. Voltage and current are the derivative of voltage, or voltage is directly proportional to the derivative of current. And when you remove the constant of proportionality, then you replace that by inductance, and the unit of inductance, of course, is Henry, after Joseph Henry, who, of course, discovered the properties of inductor. So this is the current. Let's go ahead and solve one problem for the voltage and one problem for the current. So let's say you have an inductor. Inductor, let's say, is 3 Henry. And the current that is passing through the inductor is given by 2 cosine 5000 pi t plus 27 degrees. And we can call this current in milliampere. What would be the voltage induced in the inductor, let's say? And we can use anytime voltage induced at time t is equal to 25 millisecond. So we are going to use the voltage and current relationship of inductor. We know that the voltage across the inductor is related with the current using the derivative of the current. And we're going to go ahead and take the derivative of the equation of current that is given to us. And I'm going to bring this 2 outside. So I'm going to make this 2L and cosine 5000 pi t plus 27 degrees. And that is in milliampere. So what I'm going to do, I'm going to use this 2 and I'm going to do 2 milli outside. So let me make this up a little bit. So I'm going to do 2 milli here, 2 exponent negative 3 times L. 2 milli. And we take the derivative of that, which is going to come out to be negative cosine of the angle and then the derivative of the angle. So that's going to be negative 5000 pi sine of 5000 pi t plus 27 degrees. And then we're going to go ahead and plug in the time. So one thing, it is important that make sure that change this to radians before you plug in the value of time. Because half of your angle is in radians, 5000 pi t, and half is in degrees. So make sure you cannot add degrees into radians. So make sure that convert this half that you have into radians first, and then add whatever you are adding basically. So let's go ahead and let me open my MATLAB. Let's see. So my L is 3, and my time is, I believe it was 23 milliseconds, if I remember correctly, 25 milliseconds. 25 milliseconds. Okay. So my V at 25 milliseconds is going to be 2 exponent negative 3 times L times 5000 pi times sine of 5000 times pi times t plus 27, convert into radians, multiply that by pi, divide by 180. And of course, we have a negative sign. Now, remember, negative and positive sign just represent the polarity. So many times you just have to calculate the magnitude, not the polarity. So if you're calculating the magnitude, just the magnitude is good enough. But negatives, if the value comes out to be negative, that means polarity across the inductor is opposite than what it is shown. So I believe this is 2 exponent negative 3 times L, 5000 times pi sine 5000 pi t plus 27 pi by 188. So 42.788. And that is at 25 milliseconds. And I can put this work as well. All right, so we can do another problem in which we will calculate the current based on the given voltage. So let's calculate problem number 2. Let's assume use lighter color. Let's assume that the voltage across an inductor is given as and this is the voltage, this is the time. Let's assign some values. Let's say this is 2 volt. Let's assume this is 5 volt. 2 seconds. 4 seconds. So let's assume that this is the voltage that is applied across an inductor. Or this is the voltage that is induced in an inductor. So let's say the inductor L is given as 5 Henry, and you have, or let's do a smaller inductor, 5 millihenry maybe. Inductor is 5 millihenry. And you need to find out how much current is passing through the inductor when the voltage is given by this waveform. Voltage across an inductor. So voltage across an inductor, we write it down as a piecewise linear function first. It is 0 for t less or equal to 0. 2 volt between 0 and 2 seconds. 2 volt between 0 and 2 seconds. And then the equation of the line to represent what will be the voltage. So for this equation of the line, we have V minus V1. So V minus 2, VL minus 2 equals V2 minus V1, 5 minus 2 over X2 minus X1, or T2 minus T1, 4 minus 2, times T minus T1. T minus the initial time, which is 0. So we have VL is equal to 5 minus 2 is 3, 4 minus 2 is 2, so 3 by 2, T plus 2. That will be the equation for your voltage between, this is the equation for the voltage between 2 and 4 seconds. So let me fix it, because that's going to be 5 minus 2, 4 minus 2, T minus the initial time, which is not 0. That time is 2 seconds. This 2. So VL minus 2 and 5 minus 2, 4 minus 2 is the time, and the initial time is 2, so T minus 2. So that's going to be T minus 2. So this 2 will be cancelled. No, this 2 will not be cancelled out because it's going to be multiplied by 3 by 2. So 3 by 2, so that's going to become negative 3. Fix this. So that's going to become 3 by 2 times 2. So that's going to become negative 3. And negative 3 and plus 2. Negative 3 plus 2. So we're going to have 3 by 2 T minus 1. And just to make sure that your values are still valid, put T is equal to 2 over here. Your answer is going to be 3 minus 1, which is 2 volt. And then put T is equal to 4. That's going to be 3 times 4, 12. 12 divided by 2, 6. 6 minus 1 is 5. So this equation represents the line equation with the correct values of the voltages. So we have 3 by 2 T minus 1 between 2 and 4 seconds. And then we have 5 volt after 4 seconds. So this is our piecewise function for the voltage. And now we have to find the current for each of these time instances, time periods. So t less than 0. Since voltage is 0 and initial value of current is not given to us, we can assume that the initial value of current is also 0, and therefore our initial value, our current before t is equal to 0 is going to be 0. Remember, ILT is equal to, in this case, 1 over L from negative infinity to t VLT dt plus IL at the initial value, and we take that initial value at negative infinity or whatever the initial value is going to be. In this case, we are assuming that before t less than 0, we are going from negative infinity to 0. And that's going to give me 0 ampere. Now, between 0 and 2 milliseconds or 2 seconds, we're going to go ahead and integrate 2 volt. Zero 50 and 2 times dt plus the value of current at 0, 0 positive, 0 negative. Now, for capacitors, we discussed that capacitor voltage cannot change instantaneously. For inductor, the same is true for the inductor current. Inductor current cannot change in an instant of time. So whatever the value of current just before the change is happening, the same value of current is going to be just after the change has happened. Inductor voltage can change instantaneously, similar to capacitor current can change instantaneously. So it's opposite in inductor with respect to the capacitor. But inductor current cannot change instantaneously. So if the value of the inductor current just before 0 was 0 ampere, this will still be 0 just after the change. So the equation that you will have will be 2 over LT. That's the equation of line from 0 to t. And now the third time period is 2 to 4. So first, what we are going to do, we are going to find the initial value of inductor current for the next cycle at the initial at the beginning of the interval. So from 2 to 4, what is the value of current at 2 seconds? So IL2 will be equal to 2 times 2, 4, 4 over L, and L, what did I take? The value of L is 5 millihenry. And that's going to make the current to be like kiloamperes. So let's go ahead and then just take it to 5 Henry instead of 5 millihenry. So then the current value don't go out of the roof, 5 Henry. So 4 over 5, basically. Four over 5. That's the initial value of current at 2 seconds. And now we're going to go from 2 to 4 seconds. So 2 to 4 seconds. And for that, we're going to go from 2 T VLT dt plus IL at 2 seconds. Okay, the equation for the voltage is the line equation, 3 by 2 t minus 1. dt, and the value of the inductor current at 2 seconds we calculated was 4 by 5. 4 by 5 or 0.8 ampere. So let's go ahead and calculate that. 3 by 2 and the so t squared, half t squared, so it's going to become 3/4 t squared and minus 1, so minus t 2 t plus 4 by 5. So we're gonna have 3 by 4 t squared and then minus 2, so that's gonna become 4. 4 and 4 will cancel each other, so that's gonna be -3, and then minus t, and then minus, we're gonna do 2, so that's gonna become minus or minus plus 2. And I have plus 4. So my equation is a quadratic equation or parabolic equation for my current. -3 plus 2 is -1, and -1 plus 4 by 5 is going to be -5 plus 4 is -1, so -1 by 5, right? -1 by 5. -1 plus 4 by 5, -5 plus 4 by -1 by 5. Okay, that is our equation for the current between the time when the voltage is changing linearly between 2 and 4 seconds. Now from this, we can calculate what is the value of current at 4 seconds for the next interval. So IL4 is, let's go ahead and calculate it. T is equal to 4, and IL4 is equal to 3 by 4 times t squared minus t minus 1 by 5, 7.8. 7.8. So that's my initial value for the next phase. And the next phase is that the time is greater than 4 seconds. And when the time is greater than 4 seconds, then my voltage is 5 volt. So ILT is 1 over L. Did I? Oh, I forgot 1 over L over there. Interesting. 1 over L, 1 over L, 1 over L. Over L, and that is going to change things a little bit. So let's go ahead and calculate that. All right, and L was, I believe, 5 Henry. That's going to be 3 over 5 times 420, 3 over 20 t squared minus 3 over 5 minus t over 5 plus 2 over 5 plus 4 over. So I have 3 over 20 t squared and minus t over 5, and then these 3. 5 is the common factor, and I have negative 3 plus 2 plus 4. So negative 3 plus 2 is negative 1, and then plus 4 is plus 3. That is going to be my current. And then the value of current at the beginning of next interval, which is at 4, IL 4 seconds, is going to be, again, let's go back and do that. Okay, so L is already there. Oh, not that. There's 5. No, I don't need L, actually. I have the equation anyways. Okay, so I have IL 4 seconds is 3 by 20 times, oh, I didn't define T. T is defined force. So IL4 is 3 by 20 times T squared minus T over 5 and plus 3 by 5. So 2.2 ampere. 2.2 ampere. All right, this initial value we're going to use in the next step. And the next step is that time is greater than 4 seconds. So IL t will be equal to 1 over L integral of, now this is going to start at 4 t, and the value of that is, what, that 5 volt t plus IL at 4 seconds. Let me go and check. The value is 5 volt. So 1 over L, and I can put down 5 over L actually. 5 over L integral 4 to t dt plus 2.2, which will give us 5 over L t 4 to t plus 2.2, which will give us 5 over LT. And L is 5, so I can just write down T. So that's T. And then we plug in 4, so minus 4, 5 over L will be 1, plus 2.2, which will give us T minus 1.8 ampere. So these are the equations for your time for the different intervals that we see, starting at 0, then it's going to become a line equation 2 over LT, which is equal to 2 over 5t. And then so it's going to be a line, and then it's going to be a parabola or parabolic equation or a quadratic equation, 33 over 20t squared minus t over 5 plus 3 over 5. And then finally, again, it's going to become a line equation t minus 1.8. So that's a calculation of current from the given voltage. As far as power in an inductor is concerned, Remember, power is the product of voltage and current, and voltage is given as L dIL over dt times IL, which we write down usually LIL dIL over dt. Or if you want, you can go ahead and plug in the current expression and write it down in terms of voltage as VL times 1 over L integral of VL from the initial time t0 to t dt plus the inductor current at the initial time. The first equation is used very commonly, LIL IL over dt. And from power, we can calculate how much energy is stored in an inductor. Now, energy is stored in an inductor in the magnetic field of the inductor. So the energy stored is the rate of change of energy or rate of change of work represents power. So power is dW over dt. W stands for the work or energy. So dW will be equal to P times dt, and P is L I di over dt times dt. Dt will cancel. And then we can integrate both sides. We can assume that the initial work is WT0 and then W at time t, dW. And then the initial current is I at t0 and then I t. And this will give us the equation for our power. The Wt minus Wt0 is equal to L. It's going to be half I squared. So half I squared t minus half I squared t0. If the initial current is 0, the energy stored will be 0 as well. Therefore, if we ignore Wt0 and IT0, we get the usual energy equation, that is W is equal to half L I squared. And this is the equation that is used to calculate energy stored in an inductor at any instant of time t. All right, let's do one more problem. Let's say we have a resistor and an inductor. Inductor is given as 3 Henry. Voltage across inductor is VL. Resistor is given as 0.1 ohms. And this is a current source, AC current source rather. Its value is IST is 12 sine pi t over 6. And we have to find out first the two voltages. Now, since this is a single loop circuit with a current source, the current of the current source is going to be the same passing through. both components. So using Ohm's law, we can write that down, the voltage equation as IS times R, and that is going to be 12 times 0.1 is 1.2, 1.2 sine pi t over 6 volt. And then you can find out at any time instant what is going to be the voltage by just substituting that value of time. The voltage value across the inductor, we know that is equal to I over dt. So that is L L di over dt. And the equation is 12 sine, so I'm going to bring 12 outside, 12 L di over dt, sine of pi t over 6. So that's going to give you 12L cosine of pi t over 6 times pi by 6. Pi by 6 times cosine of pi t over 6. And well, the L value is 3, so you can easily write this down as 6 times 2 is 12, so 2 times 3 is 6, so 6 pi 6 pi cosine pi t over 6 volt. All right, number 3 is energy stored in the capacitor, expression for that. I simply have Li square L times I square. 12 square is 144, so 144 sine square pi t over 6. And then that can be simplified. Energy is in joule, and then you can put down any value, any time instant to find energy value at that time instant. All right, let's see how much power is dissipated in the resistor. So PR T is equal to IS squared times R. So 144 times 0.1 is 14.4, 14.4 sine square pi t over 6 watt. That's how much power is dissipated in the resistor. And at any time again, you can find out the power dissipated at that instant of time. And if you want to find out the total energy dissipated in the resistor, then you can integrate the power with respect to time between two limits. And that's going to give you the total energy between those two limits, as how much power is dissipated between two time instances. So, all right, next thing is if a circuit is operating at a steady state, that is, if the inductor is acting as a short circuit, then you're going to find different values of voltages and current. Assume in the following circuit that the inductor, or assume in the following, let me read. Assume the following circuit is at the steady state. Let's write this down. Assume the following circuit to be at the steady state. Steady state means that all the transients are gone. That is, if you have inductors or capacitors, they are fully charged. And capacitor is acting as an open circuit for DC, and inductor is going to be acting as a short circuit for DC. They are fully charged. Acting as to be at the steady state, that is, inductor is acting as a short circuit. Calculate. See, let's put a circuit and then decide what to calculate. Assume we have all right. So I put a couple of inductors. So we're gonna do that is inductors are acting as short circuit. Let's assume we have source voltage 10 volt, R1 is 10 ohm, R2 is 22 ohm, R3 is 43 ohms, and R4 is 97 ohm. L1 is 20 millihenry, and L2 is 55 millihenry. So the circuit is operating at the steady state, which means both inductors are going to be acting as a short circuit. Okay. VR1, IL1, IL2, and VR4. So calculate first VR1. Okay, so again, there's no calculation for VR1 because if inductors are acting as a short circuit and that L1 is in parallel with R1, then of course the voltage across the resistor and the inductor both are going to be zero. Since L1 is short. All right, second, how much current is passing through inductor 1, IL1? So IL1 is going to be the total current coming out of the source. Again, if you short that L1, R1 is going to be gone. So your circuit basically at the steady state is going to look like short R2 and R3 and R4. This is your circuit is going to look like at a steady state. At a steady state. Vs R2, R3, and so this IL1 is the total current coming out of your power supply, which can easily be found by combining all the resistors and calculating the current. So that is going to be Vs over R3, R4 in series in parallel with R2. So R2 parallel with R3 plus R4. And that current can easily be found out. This where the Vs is 10. I'm not going to put R1 since we are not using R1. R2 is 22. R3 is 43. R4 is 97. So IL1 is Vs divided by the parallel combination of R3 plus R4, R3 plus R4, and R2. 0.5260 ampere. 0.526 ampere or 526 milliampere. Okay. Next is we have to find IL2. And again, IL2 is the current passing through R2. So again, we know the total current, and we can apply current division between R2 and R3 and R4 to figure out what IL2 is. So let's apply current division. IL1 is our total current, and that is divided between R2 and R3 and R4. So IL1 times the parallel combination of R3, R4, and R2 divided by R2. R2 parallel R3 plus R4 divided by R2. So let's calculate that. IL2 is IL1 times the parallel combination. So RP of R2 and R3 plus R4. So comma not period. Parallel combination of that and divided by R2. 0.4545 ampere. Okay, and what else do we need? We need VR4. So VR4 can easily be found out. VR4 can easily be found out by calculating, well, a couple of ways. We can calculate what is the voltage across R2 since we know IL2, and that voltage will be across R3 and R4, and then apply voltage division. Perhaps that might be easier way to go. Or the other is that we can find out how much current is going in R4, again using current division, or simply KCL. Since we know IL1, we know IL2, then we will know what is, let's say, IR3. So we can calculate IR3 and then calculate VR4. Let's just do that. It might be easy. IR4, let's call it IR4 since we are calculating VR4. Instead of calling it IR3, we can call it IR4. IR4 IR4 is equal to the total current IL1 minus the current going into IL2. IR4 is equal to IL1 minus IL2. 0.071, so 71 milliampere, which implies VR4 is equal to IR4 times R. So VR4 is equal to IR4 times R4. 6.9286. So these are all the values for this problem. So important thing again in the problem in which you have inductor and the circuit is operating at the steady state, the important thing is that you assume that the inductor is acting as a short circuit, and then replace all the inductors by short circuit, and then solve the problem and find whatever quantities you're trying to find. Then find you find those quantities.